the application of an external voltage. It is a two-terminal device. A PN junction diode is symbolically represented as shown in the figure. The direction of the arrow indicates the conventional direction of the current. The equilibrium barrier potential can be altered by applying an external voltage V across the diode. The situation of PN junction diode under the equilibrium. PN junction diode under forward bias. When an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side is connected to the negative terminal of the battery, it is said to be forward biased, as shown in the figure. The applied voltage mostly drops across the depletion region, and the voltage drop across the P side and the N side of the junction is negligible. The direction of the applied voltage V is opposite to the built-in voltage V0. As a result, the depletion layer width decreases and the barrier height is reduced. The effective barrier height under the forward bias is V0 minus V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value, and only a small number of carriers in the material, those that happen to be in the uppermost energy levels, will possess enough energy to cross the junction, so the current will be small. If we increase the applied voltage significantly, the barrier height will be reduced and more number of carriers will have required energy. Thus, current increases. Due to the applied voltage, electrons from N side cross the depletion region and reach P side. Similarly, holes from P side cross the junction region and reach N side. This process under forward bias is known as minority charge injection. At the junction boundary, on each side, the minority carrier concentration increases significantly compared to the location far away from the junction. PN junction diode under reverse bias. When an external voltage V is applied across the diode such that N side is connected to positive and P side is connected to negative, it is said to be reverse biased. The applied voltage mostly drops across the depletion region. The direction of the applied voltage is same as the direction of the barrier potential. As a result, barrier height increases and the depletion width widens due to the change in the electrical field. The effective barrier height under the reverse bias is V0 plus V. This surpasses the flow of electrons from N to P and the holes from P to N. Thus, diffusion current decreases enormously compared to the diode under forward bias. The circuit arrangement for studying the VI characteristics of a diode is shown below. That is, the variation of current as a function of applied voltage. The battery is connected to the diode through a potentiometer or what we call rheostat, so that the applied voltage to the diode can be changed. For different values of voltages, we may note the value of current is noted. A graph between V and I is obtained. After studying the graph, we may note that in the forward bias measurement, we use milliammeter since the expected current is large, while a micrometer is used in reverse bias to measure the current. We can see that in the forward bias, the current increases very slowly or almost negligibly till the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases significantly, or we can say exponentially, even for a very small increase in the diode bias voltage. This voltage is called threshold voltage or cut-in voltage. which is approximately 0.2 volt for germanium diode and 0.7 volt for silicon diode. For the diode in the reverse bias, the current is very small, approximately in microammeter, and almost remains constant with the change in the bias. It is called reverse saturation current. However, for special cases, that is, at a very high reverse bias or breakdown voltage, the current suddenly increases. Let us take an example. The VI characteristic of a silicon diode is shown in the figure. Calculate the resistance of the diode at A. ID equals to 15 milliamperes and B. VD equals to minus 10 volts. Solution. Considering the diode characteristics as a straight line between I equals to 10 milliamperes